All right. Whoops. Okay, there we go. Got it. My mark. All right. So we're fortunate we have 3 lectures left. Hopefully this will take 2 lectures, but we've got a little extra if I need to go slow, so I apologize in advance if I'm not perfect here. We want to talk about pressure and fluids. Okay, and I believe this is on page, what is it, 127. And before we get into it, I kind of want to just give you a big overview. You don't need to write down what I'm about to do here. I just want to show you where we're going so that you can hopefully pay attention. Fluids is a very complex topic. We are going to restrict ourselves to some of the simplest parts of it. So we're not really going to teach you all of the complexities of fluids. We're going to teach you the very, very simple, basic stuff. So we're going to start out by talking about definitions, units, and some simple calculations. All right, and that's how we're going to start today. Keep it simple to start. Then I'm going to do some fluids at rest. Some of the things that happen in fluids at rest, some classic problems that you may have seen before. There are things called U-tubes. Now, this is old school, like 1800 U-tube, where it's literally a tube shaped like a U with some fluid in it. And you can have different types of fluids in here, and they might stack up like oil and water and things like that. So this is one example of a fluid at rest. And remember, you don't need to write any of this down. I'm just giving you a big picture. There's hydraulics. Let me give you an example of hydraulics. Let's say you have 2 pistons. One of them is a different diameter than the other. There's a simple hydraulic system. All right? We make the party. Whatever, at least they're having fun. Okay. And then the last one, I should make them sit in here and do physics, right? That'll calm them down.
Is that your kids, person?
No, not my kids.
Oh.
That's cool. You know, I used to run around the campus at my school, in my hometown too. I'd just run around and like press every button I could and try and break stuff. But yeah, buoyant force. Let me give you an example of a buoyant force real quick. So this is like objects floating, right? So that's what this aquarium over here is for, where we need to get stuff floating. Right? A buoyant force, we can talk about the variations on things like this. Here's a simple boat. Now it's an iron ore tanker. Right? Right. Just a little bit that way. So maybe we want to talk about the physics involved with boats. And obviously we might start simpler with how do you make a raft float. But we can talk about buoyant forces. Now notice these fluids are not perfectly at rest, but we're going to assume that they're approximately at rest, all right? So that's why I'm throwing these in the fluids at rest category. Finally, get back up here. Oh, here we are. Fluids in motion. Now, fluids in motion could not be more complex. I argue it's probably, it's just extremely difficult. So what we're going to do is, rather than talk about the general properties of fluids in motion, which could include turbulence and all kinds of things. We're going to talk about ideal conditions. So non-viscous, meaning no drag, right? Which is not true. Irrotational, no turbulence. So what I meant by doing the simplest possible cases, maybe we could call this laminar flow. We're going to do, these are some of the words that describe ideal fluids. And in particular, we're going to analyze problems like this, where you have a pipe. There's a center line on this pipe. Again, we're going to come back to this next time. There's a center line on this pipe. And there's a difference in elevation. In particular, the fluid flowing into the pipe, we could call that V1. And there's a diameter associated with this side of the pipe. I could call that D1. And there's going to be fluid speed coming out the other side. And there's a different diameter. And we could talk about the relationship between all of these parameters for fluid flow in a simple pipe. Now, some applications of that you might be thinking about would be blood vessels, right? The aorta, maybe some capillaries. Oh man, I might have to say something to these kids. Hold on. Hey, don't forget, we got a class going on. You guys just kind of don't scream around here. All right. Got it? Just kind of keep it down over here, all right? Thanks. It's going to be distracting all day. All right. But so we might deal with problems like this. Another classic one, maybe you can imagine this. A bucket, another bucket. This one's sitting on the ground. This one's maybe up high on a lab jack. There's some fluid flow in here. Oops, sorry, some fluid in here. Purple. And then maybe we're going to transfer it over to here with a tube. Right? And so what is the name of this device? A siphon. So this is related to this simple pipe problem. So we're basically going to restrict ourselves to simple problems like a siphon or this fluid flow in a pipe problem where you have some fluid in here and it's changing elevation. So that's our goal for what we're going to try and talk about in this. But then after all that, there's crazy stuff. Now, you know me, right? I'm pretty crazy. If I'm calling it crazy, it's going to be pretty crazy. So there's going to be a whole bunch of really weird demos. And I don't know why, but I have this passion for trying to show you demonstrations on fluids. And this, for me, was the hardest chapter of the book to write because you have to speak very carefully. You have to pay attention to all these different conditions here. And what I hope to do is, after we get through all this stuff, including the crazy stuff, I will try to make it painfully clear what you really need to know for testing. Got it? So just make sure we hang in there. You're going to learn a lot of stuff. There are just so many interesting applications in this chapter. I'm going to try and show you as much as I can so that you remember it. And they say that if you see the demonstrations, you remember it for life. All the calculations you forget in 6 months. So I hope by showing you some of the applications and the weird stuff that can happen, you find it slightly interesting. And maybe that first question on your exam, when you have to write down some problem that says, oh, what did I find interesting? Hopefully you could write down one of these weird topics for that is what I was thinking. So, all right, that's our goal. You ready to get to it? Okay, let's start then by talking about some equations and definitions. I'm going to start on the next whiteboard. I think this is gonna be a fun time. So make sure you come to class next time, right? You can't see some of these demos on Zoom. You just have to see them in the real world. Okay, we're gonna talk about pressure. I'm gonna use capital P. So to indicate that it's capital P, I'll put a line underneath it. It's force over area, or F over A. Immediately, let's talk about units. What are the units of force? Newtons. What are the units of area? Meters squared. This is a convenient unit. We call it a Pascal. So physicists don't use ATMs. Usually. They might, and we will on occasion. But we like to use Pascals because physicists often care about forces. And so this is the unit that matches up to force easily. So far, so good? So in chemistry, what are the units you use for pressure? In chemistry, ATM. It turns out 1 ATM, we call that standard atmospheric pressure. In terms of pascals, that is 1.013 times 10 to the 5th pascals. If it helps, I like to think of it this way. Imagine you're sitting on the ground. Your surface area, if you lay down on the ground, is approximately 1 meter squared. Or you could imagine that's about like this, right? It's not exactly 1 meter by 1 meter, but it's pretty close. Are you guys okay with that? It's about 1 meter squared. Now, if you think about it, what does this mean? This is about 10 to the 5th. So, right, I'm going to use 10 to the 5th. There are 10 to the 5th newtons of air weighing down on this 1 meter squared. That's what it means. So if you think about the weight of all the air molecules going up to the sky in the box defined by this 1 meter squared area, there's approximately 1 times 10 to the 5th newtons of air weighing down on each meter squared on the surface of the earth. Cool with that? That's where these numbers are coming from. Everybody okay with that? Question?
So is that just like weighing down on top of something, or is it from like every?
It's from every side too. So this is the thing. That's a lot of newtons, right? Now, when you think about it, there's some of this is on the front and some of this is on your back. It should be, the air pressure is not changing that much from this side of my body to that side. Now, obviously, if I swoop my hand really fast, I create turbulence and lower the air pressure there. We're not talking about that. So right now, I'm assuming on average, the amount of air pressure on this side of me and that side of me is the same. That's why I don't feel pushed sideways just by air, but it is pushing this way, that way. Right now, it's pushing up on the bottom of my thigh, right? It's pushing on every direction. Good? All right, good question. All right. What else do I want to say about that? Now, there's a bunch of different units. Maybe you've heard of bar, torr, millimeters of mercury. Maybe you've heard, what else do I want to use here? Is there another one I wanted to use? What's the other famous unit of pressure? These are all units of pressure. You're pumping up a bicycle tire. What's that?
PSI.
PSI. Pound per square inch. So now, let's get real here. I'm going to use either ATM or pascals on the test. But just for reference, and I think I have these all written up here. I can't remember most of them. I forget what a bar is, but these two are approximately 1/760th of an ATM. More on that in a minute. They're not exactly the same. There's a comment in there. At one point, they were exactly the same, but then they were redefined. And now I think one of them, I think a torr is slightly different than a bar, right? Now, pounds per square inch. Does anybody happen to know atmospheric pressure in pounds per square inch? It's on there. I think it's 14.7 PSI equals 1 ATM. Now, I'm going to cheat a lot of times and just round this to 15 PSI. It's no other part. Okay. Guys, okay with that? This is a handy one to know, just so you know, right? Because in the real world, we often use PSI. All right, I got to say something again. Sorry. It's killing me. Okay, guys, I got to call the cops if you're going to do this. Can't be on the class, okay? I appreciate you. I appreciate you. I want to have a good time, but go play somewhere else, all right? Bats come out again, I'm calling the cops. All right. All right, so let's talk about this. Pressure, force, area. Let's look at a simple example here. Where are we? We're go to this one, I think. Okay. All right. So let's take a look right here. Let's say I'm doing push-ups, right? Obviously, I'm cheating and doing easy push-ups here. What's going to happen to the force on my hands if I switch to fingertip push-ups? Does the force exerted by my hands change? Yes or no?
No.
No. Does the pressure change? Yes. This is why it's more painful, right? You're applying the same amount of force, but you're using less area. Instead of a whole hand, you're using just your fingertips. This is why I stopped using high-heeled shoes years ago. Right? Oh, I switched to flats. Anyways, that's my attempt to make a joke. It didn't work. That's problem 14.1, people. Okay, so we're already done with the problem. That's sweet. Another example of this, right? You're standing on a scale and you lift a foot, right? Right now, did the force exerted by the floor on me change? Right, so I'm standing here, 240 pounds of me. When I lift my foot, instead of having 120 and 120, I've got all 240 on one foot. Does the pressure change? Yes. The force doubled. In this case, the area stays the same, so the pressure goes up. So far, so good? Right? The force per foot was 120. Now the force per foot is 240. All right. What else? Snowshoes. Most of us here probably don't do a ton of snowshoeing. But here's what a snowshoe kind of looks like. Here's your foot. Let's say those are some boot laces. What is the point of a snowshoe? That's your leg. What is the point of a snowshoe? When you put a snowshoe on your foot, what happens? What is the snowshoe doing for you?
Stop your foot from sinking into the snow.
You don't sink into the snow. Why?
Versus the pressure.
What's that? It decreases the pressure. You still have the same amount of force. Actually, you have a little bit more because you have your body plus the weight of the snowshoe, but that's negligible. So it's approximately the same force, but you get this much larger area. If you apply the same force of a much larger area, you're less likely to sink into the snow. Got it? Snowshoes. All right. Cool. I'd like to do a real problem. I want you to start looking at 14.4 while I erase the board. Okay, I'm going to erase the boards here. Hopefully that showed up. Okay. I'm just erasing really quick. But I scared the crap out of those kids, huh? I feel bad, but you guys got to learn this stuff too. All right. This is a very contrived problem. It's not realistic, but it gets us started. So my apologies if this problem offends you. In its lack of realism. We've got a building. Kind of looking at a slanted view of it. It's sitting here on the ground. We just have a plain old rectangular building. We're going to completely ignore any realistic roof. It's going to be completely flat. So we're going to concern ourselves with this roof. Okay. We clear this green area down here is like the grass around the building. All right. We're told that I think this side is 10.0 meters. This side's 15.0 meters. I hope I got the dimensions right. Yeah, it's pretty close. And I'm going to model this roof as a thin slab like this. This is a slanted view. I'm going to do a pure side view over here as well. What are the forces that are acting on this roof? Well, what's one force that acts on any object, pretty much? mg. So there's going to be a gravitational force, assuming it's a regular slab. Let's assume this is right at the center. There's going to be an mg. Are there any other forces on the roof? There's some sort of force. Maybe the walls are providing that support. So how about I just say, I'm going to put a dot here and say force from the wall And I'm going to divide it by 2, and let's just assume it's supported on the 2 ends. Again, I said this is a very contrived problem. There's going to be some force from the walls. And what I'm saying is, let's just assume it's supported by this wall and this wall over here. So there's a force on each side, let's say, holding it up. Everybody okay with that? So I just took the net force from all the walls, divided by 2, stick it on each side. Are there any other forces acting on this? There's 2. Here's the new ones. We're told that there's a storm coming. And outside, there's air. And the pressure on the top surface or outside is equal to, what does it say? It says atmospheric pressure has dropped by 15%. What does that mean? The pressure is outside. It's not 1 ATM anymore. What is it? It's not 75, but 85, right? 100% minus 15% is 85% of 1 atmosphere. Now, because we're doing physics, we're immediately going to convert this to pascals, but for now, it fits on the board better. Is everybody okay with that? Inside the building, we are told inside the building was sealed when it was at normal atmospheric pressure. So inside, I'll call this beneath the slab or bottom, is 1 ATM. So the air inside was sealed when it was at 1 ATM. Okay. And if you recall, 1 ATM, this is a number we're going to use so often. Sometimes we call this P subscript 0. So this is standard atmospheric pressure. Our default is going to be, call that P0 all the time. And recall that was 1 times 10 to the 5th. 1.013, if we need to be more precise, times 10 to the 5th pascals. And if you recall, a pascal, what were the units equivalent to? A pascal was a Newton per meter squared. That's going to be handy. We're not going to want to use ATMs for physics problems. We're going to want to use this new unit, pascal. Now I want you to think about this. What's happening inside? There's a whole bunch of air molecules, not just billions, not just billions of billions, but billions of billions of billions of billions of billions of billions of billions, etc. Many, many air molecules. Now what's happening? These molecules are moving around. Some of them are going to bump into the roof and be pushed downwards, right? Every time one of these molecules hits the roof and is reflected downwards, there's a small force. Agreed? If we add up those forces, it relates to the pressure. So there's a pressure upwards, and there's a force due to P bottom. Does that make sense? At first, you might think this is negligible. Turns out it's not. There's also a force downwards due to P top. The air molecules on top are doing the exact opposite. They're being bounced upwards, right? So when these air molecules are bouncing off the roof, they add up to a force. Hey, what's up, Alfredo? Yeah. Pink. Be right back. Yeah, no problem. All right. So I want to remind you of something. What was our definition of pressure? Can someone remind me our definition of pressure? It was what over what? Force over area. Let's flip this. What is the force going to be? If we know the pressure and we want to get the force. So this is the trick we're going to use in physics. We can take these pressures and convert them to forces and shove them in our free body diagrams as long as we use force as pressure times area. Okay. Let's write down the force equation in the y direction. Oh, by the way, this pressure drop of 15%, I was able to find one weather report where this happened. And it happened during a very violent storm. Now we're going to kind of, so to be clear, this is about as an extreme of a case as I could think of. But it is, in theory, physically possible in the real world. But any bigger change than this is pretty outrageous. All right, just so you know. Okay, let's do the forces in the y. You agree there's going to be F wall? Thanks. Right on. Have a good one. If you need it again, just come right back. There's going to be mg down. All right, you agree that F wall is these two put together? And then there's going to be I'm going to call it force P bot minus force P top. Generally speaking, what's a good acceleration value for a roof? Hopefully 0, which means it's not moving, right? So you were thinking of this term, right? That's the, yeah, sorry. But hopefully our roof is not accelerating. That's what would be nice. So we're going to set the acceleration to 0 here. Now, in this case, I want to show you something cool here. Actually, let's do this first. Let's get some numbers here. Let's get the numbers for force P bot and force P top. Pressure bot times area. Well, we know the pressure on the bottom is 1 atm, so that one's easy. The pressure is basically 1 times 10 to the 5th newtons per meter squared. There's some extra sig figs there. The area, what's the area of this particular slab? 150 meters squared. Notice we get units. Can you punch this in for me? I'm going to get my calculator out. We're going to use it all day. Oh, there it is. 1.013 EE5 times 150. 1.520 E7. 10 to the 7th newtons, approximately. 1.5 times 10 to the 7th newtons. Let's get P top as well. And then just humor me here. That's going to be pressure on the top times area of the top. Do you agree that should be 85% of this? Right, the pressure is 85%, so the force should also be 85%. So I'm just going to slap a times 0.85 on there. So times 0.85. 1.292. Choosing my thick face and rounding. I think that's about right. Everybody okay with that? The mass of this roof was what did I use? 18,000 kilograms. So let's get that done too. The mass, we're told that the mass of the roof was 18 times 10 to the third kilograms. So mg is going to be 18 EE3 times 9.8. All right. 1.764 times 10 to the fifth newtons. We're just kind of highlighting these numbers. I want to show you something here. That's a very heavy roof. Do you agree? But look at the math. I'm going to show you where this shows up. 10 to the fifth. That's 100 times smaller than 10 to the seventh. Agreed? You buy that? That means this digit right here, the weight makes a difference of about 1 in the third digit. Maybe 2 in the third digit. Do you agree the weight of the roof is actually negligible in this case? Think about that. During inclement weather, if the pressure really does drop by 15%, the forces associated with the weight of the roof are negligible. That's pretty scary. Have you guys lived through a tornado ever? Okay. I grew up in Illinois. We had them hit the hometown. You're hiding in the basement, scared out of your mind. Yeah, it's crazy. So it's a little weird. But check this out. Which force is bigger? The upwards force or the downwards force? The upwards force. Which way is the force from the walls? Downwards. Think about it. This blue force is bigger than this red one by 15%. The weight of the roof is negligible compared to those two arrows. The weight of the roof is negligible. The walls have to hold the roof down in a tornado. This is why your roof goes blowing off. But there's an easy way to fix this. If you don't want your roof to go flying off in a tornado, what's something you could do? Open the windows and the pressure will equilibrate. And then you don't have these big pressure differences. So the problem with pressure is not pressure itself. We discussed this, right? There's a big pressure on each side of me right now. It's pressure differences that give rise to damaging forces. And let me show you where that shows up in the math here. Just stick with me here. We're going to discover that this must be negative. Right? If that roof is not going to fly off, that's pretty crazy. So in this situation, this is outrageous, but it gives you an idea of tornado physics, all right? And let's be clear here. The wind force and the fact that the fluid is moving complicates this tremendously. This is a total nonsense problem, but it gives you a feeling for the correct types of physics that are going on, okay? In reality, what's happening is the fluid is moving, and that's going to change our analysis completely. We completely ignored any lateral forces. That's like, okay, this is so far from reality. It's only good for getting numbers and the sizes of things. That's all it's good for. But that said, look, we're going to get this force from the walls. We expect that to be a negative number. We're going to get this mg. We expect that to be negligible. And when I plug this in, I want to point this out. We're going to get plus area, oops, P dot times the area minus P top times the area. And all that's going to equal 0. Well, if I combine these two terms, look what we get. We get pressure bottom minus pressure top times area. This force right here It has to do with the change in pressure times area. So typically, this is what I was saying a minute ago. What really matters in the forces after all is said and done is the pressure difference on two sides of a plate. That is important to get out of this problem. Are you guys okay with that? That's all I really wanted to do with this problem, was motivate the reason for caring about these pressure forces, because they're enormous, right? The bigger your area, the bigger the force. 10 to the 5th adds up really fast. And then it's differences in pressure that matter. Good enough? Okay. That's a very oversimplified problem, but it's kind of interesting. All right. I'm going to let you read page 128 on your own. Okay. Let me rephrase. Problem 14.5. Let me get on the right screen here. But I do want to kind of mention a little bit about this. So I guess we're doing a little discussion of it. So talking about 14.5. Let's imagine that you fill this thing with mercury, okay? We have mercury in here. Right? And now what you could do is you could take a test tube and invert it. Maybe it's a very long test tube. Okay? And what's going to happen here is you could connect this somehow to a pump and evacuate it. We're going to evacuate most of the air. And by that, I mean the pressure is approximately equal to 0. Okay? And here's what happens in this scenario. If we have negligible pressure inside of here, but we have atmospheric pressure outside, there's air outside and not much air inside. Let's think about what is the downforce on the mercury inside the tube. If there's approximately 0 pressure here, how much is the lack of air pushing down? It's not, right? Now outside, do you agree this air is exerting a giant downwards force? So there's pressure from the air outside. Right? What is that going to do to the mercury? It's going to push it upwards, and the mercury is going to start filling this up. Outside, the pressure is atmospheric pressure. It's 1 atm. Okay? Well, inside there's no pressure. It turns out the height of the mercury column is about 760 millimeters, or 0.76 meters. So the numbers, this is a barometer. If you have this thing sitting in your house, if the atmospheric pressure drops, what's going to happen to the height of the mercury column? It's going to go down because there's not as much force pushing the mercury up. This is a barometer. It tells you the pressure. And so if the height of the mercury column is exactly 760, we'd say, oh, it looks like it's normal atmospheric pressure. Okay, if it lowers, we know there's less than standard atmospheric pressure. Cool? That's where the units millimeters of mercury come from. So this is a convenient way to measure pressure in the real world, as long as you don't spill the mercury and just like get sick from it. So maybe you shouldn't make one of those at home. right? Let me ask you this. Which do you think is more dense, mercury or water? Mercury, okay? So if you made one of these same things with water, what would be different? Water has a lower density. What do you think would be different? If you had a lower density fluid, what would happen to the height of the tube? Do you think it'd be a taller tube or shorter? Taller. In fact, if you made one of these out of water, it's going to go for a long ways. Hey, I teach in here. I don't care. Oh, you can't see that on Zoom, can you? Let's get this full glory here. Let's get it recorded here so I can get fired. Claim workman's comp. They're going to be going up to 10 meters. Now think about that. That's pretty tall. 10 meters is about how many feet? Ish. 30 feet. Well, wait a minute. We're saying that if you have an absolute vacuum, the height of the water column could be about 30 feet. You ever seen a tree taller than 30 feet tall? How's the water get up there? Ha. Try a Google search. All right. It's interesting. So there's something going on inside of trees which is different than this. And I'm going to leave that as a mystery for you to learn about. No. Yeah. So there's a lot of misconceptions about that. Yeah. There's a pretty good, if you do, I think the one that I thought was pretty decent was Veritasium tree. I don't know what you'd have to search for. Veritasium tree, water, pressure. I bet if you do this search, you'll find it. Try that in a web search. And there's a really good video. And you can see all these physicists and stuff and people saying all kinds of things. They're all wrong, just like I was. So I had no idea either. But the results of this video I thought were very interesting. So that's a pretty cool video. You can check that out if you want. Maybe if I'm smart, I would try to put a link to that video in the comments. We'll see if I ever remember to do that. All right. Interesting thing. The reason I might want to talk a little bit about this is where you put a pump in a system will matter. If you put a pump at the top of a well, the most you could hope to draw water is about 10 meters. Whereas if you put a pump at the bottom of the well and push things upwards, you don't need a vacuum. And so you could have water be pushed higher than 30 feet if you have a pump at the bottom of a well versus at the top. Okay, there's other issues involved. Let's just leave it at that. Okay. Yeah, let's just leave it at that. All right, so now we got a fun one. I need a volunteer that's not scared. Anybody? I want to talk about water and pressure, but I need to talk about the density of water. In particular, and I don't know if you could see this on Zoom, so let's go down just a little bit here. I have a claim. My claim is that when you have a large amount of water, the density of that water is approximately constant, even if you go deep, deep, deep underwater. My claim is that water will have this constant density as you go deeper and deeper underwater, as long as it's incompressible. By incompressible, I mean when you squeeze on it, it doesn't shrink that much. You remember we briefly talked about Young's modulus and how if you apply a force, it'll stress the stress and strain crap. Right? Earlier in the semester, I said this is not on the test, but let's, yeah, anyways. If you apply a force to water, it's going to shrink a little bit, but a negligible amount. I claim I could prove this to you by filling up this glass vessel with water. Now this was filled with water and then boiled, and we got all the air molecules, most of them out. So there's not much air in here. And then we topped it off with boiled water. So my claim is the water inside this piece of glass is not going to compress much. Are you volunteering? Come on up. You get where we're going. Here's some safeties. So my claim is, if this water is really incompressible, he should be able to hammer in these nails without breaking the glass.
Oh,
Don't screw up. Here, put these on too. Usually this works. Usually. Okay, so now let's start at that end. And then you want to make sure we're not hitting into a knot. So let's start right there. I think do you agree we're missing these holes? We're not trying to hit into them? Okay. So hit that nail and don't miss. Just start lightly tapping and just go harder and harder. Go for it. Whoops. Okay, try it. This is why we got extras. Go, go, go. Oh. Here, let's switch. Here, let's go. Try that. Hard to get it square, isn't it? Oh, here, let's do this. Let me get this one started again. And let's make sure there's no knots. Okay, go for it. Great. All right, let's give him a round of applause, eh? Right here. Now, that's pretty trippy, right? Obviously, there are limits to this, but if you can give one of these to a bunch of junior high kids and let them play with it for 2 hours and it doesn't break, it works pretty well. Now, we were lucky that time, but yeah, I've also had this shatter all over my notes many, many times. But here's another thing you can do with it. It's just a cool lens. So if you're bored listening to me, I'll pass this around. You can just take a look at it. All right. You can pass that around, look at the notes on your paper. It's kind of cool. My claim, though, is do you agree this water is fairly incompressible? So the point of all that was this.
outside glass doesn't break because it doesn't compress.
The water inside is preventing the glass from compressing, right? Because the water is unable to compress, the glass is kept from shattering. And yeah, to be fair, this is a bit of a gimmick, but it's pretty, the whole point of this was to show you the following. This is the point of that demonstration significantly. The point is supposed to be, and if you want afterwards, we could really wail on this thing and shatter it if you want. But let's do that after class. As we go under the surface of the lake, we're claiming that the density of the water is approximately constant, okay? Now, what I'm saying is it's incompressible. That's another way of saying that. And so this demonstration was supposed to make you believe me when I say that. Right? Hopefully you feel like the water wasn't compressing much because it kept the glass from breaking. That's it. Cool with that? If that is true, then I can write this next statement. This is one of the more annoying equations. We're talking about pressure versus depth. Let's say we have a lake here. Okay. Here's the surface. Above most lakes, there's air. Right? You got some air here. Unless we are told otherwise, let us assume that the air is at standard pressure. All that's going to do is change things by some percentage. And obviously, if we were gonna do any math, we would need to convert these ATMs. Actually, I don't like the ATMs for this particular one, because you'll see why in a second. Is that still on? I think so, right? Let's talk about this equation. And then are you all done with that?
Yeah.
So I got this weird little donut. Let me ask you something here. Imagine we were doing an FBD on this water molecule right here. Do you agree there would be a force downwards from the atmospheric pressure and a force upwards from the water pressure? Assuming this water molecule is not flying off the lake and ignoring surface tension, which is complicated, what should be true about the pressure above and the pressure just below this spot? It should be the same. So this is a trick. If we have air above the lake at standard atmospheric pressure, we say the pressure at the surface in this particular case is P0. Is everybody okay with that? P0 being atmospheric pressure. Now, as you go deeper, let's say we go down onto the surface of the lake, depth H. This is why I really hate this equation, because all semester long, H has meant height. Now, for this one equation and this one only, H means depth. I'll discuss more on how to avoid this inconsistency in the next class. I have a trick to show you so that you never have to use this equation. But for today, it's extremely useful. All right. There's going to be basically a chunk of water right here. And there's going to be pressure. And I think it was Ryan that was saying the pressure is actually the same in every direction here at this spot. Up, down, diagonal, sideways. The pressure on this molecule at this one spot in every direction is given by this. Pressure at depth is equal to pressure at the surface, in this case, P naught, plus rho of the fluid, G, and H, the depth. Okay. Now, let's take a second and see why these units are best. Remind me, what's a Pascal in terms of normal physics units? A Pascal is what? Newtons over meters squared. What are the units of density for a physicist? What are any units of density? Kilograms per meter cubed for a physicist. A lot of you probably did chemistry and you talk about grams per centimeter cubed. I can't help it if chemists are weird. It's a perfectly good unit. More on that later, right? A milliliter is a centimeter cubed, so it's actually really convenient for a wide variety of applications. What are the units on G? Meters per second squared. What are the units on H? Meters. So do you agree that newtons per meter squared is going to be a lot better than ATMs for this equation? Again, it's just convenient, that's all. Good? All right, so maybe we should do a problem on this one, right? So let me take a look here. Let's look at 14.7. I'm going to erase the board, so I haven't switched over. Well, let's do this. I've got to erase the board, okay? I'm going to try and leave that part up. We'll see how long this stays here. Oh, I didn't think that one through. Oops. Guess I gotta buy some tan spray paint, huh? All right. Let's go to. Come on. All right. So I want to skip to 14.7b, I think, or whatever. In this problem, we have a container here. And I believe there's going to be some water in it. I believe we're told there's 8 centimeters of water. Who cares about sig figs, okay? And we're going to have a little bit more oil. I believe it was 12 centimeters, is that right? Okay. So this is oil, and this is water. Does anybody know the density of water? Say it again. In any units? Density of water, most students remember it as 1 in units of grams per centimeter cubed. Those are terrible units for most of our problems. We want to use kilograms because Newton shows up, right? We want to avoid centimeters because Newtons show up. Now, do you agree you could use 1,000 grams equals 1 kilogram? We could use 100 centimeters equals 1 meter. You got to cube it. So this one gives you 10 to the 6th. This gives you 10 to the 3rd. The shortcut is you get 1,000. You could do this conversion at home or with Google, but I just know it. Got it? Multiply by 1,000 to get from these units to those units. All right. What is the density of this oil? Does it tell us that in the problem? We're told that the density of oil is 20% less than density of water. What's that going to be in terms of numbers and units? What is it? 800. That's it. Now, notice in this chapter, this is the second time we've used this 20% less or 15% less. The only thing I got to warn you about is, right, students get tired and they're on a test and they might accidentally say 20% of the density. That would be wrong. 20% less is 80% of. Everybody good with that? So just always be looking for that in the wording so you don't miss points or something stupid like that. What else do we know? Okay. And then the problem says, let's assume it's convenient to use 1 ATM for labeling. Have you noticed that? In most of my pictures, I label the atmospheric in ATMs because it's quicker to write it. But then when you go to do the math, you do the math in pascals. So in this case, what's the pressure right here at the surface of the oil going to be? If we have 1 atm just above it, what's the pressure right here? The same. So notice how crucial it is to draw your symbols correctly. This is capital P subscript 0. This is Greek letter rho subscript 0. If you can't draw them differently, you could write out the word rho or something to make this easier for you. But it's crucial that you get used to drawing a P, very rectangular and boxy looking, and a rho, start at the junction, curl around. Rho your density. So you got to draw your P's and your rho's correctly. Okay. All right. What was the point of this? Oh, I'm going to call this pressure right here P1. The pressure at the bottom of the oil column, I'm going to call P1. Well, what is the pressure at the top of the water column? Also P1, right? We're assuming these two pressures should be the same if they're at the same level. The pressure just above and just below the interface, we assume are the same as long as the interface is not moving. Okay. And then down here at the bottom, we're going to have pressure 2. I want to figure out P2. So how do we use this pressure versus depth equation? Well, I know that P2 should equal P1 plus density of water, G, depth of the water. Agreed? This is my pressure at the this is pressure at the surface, depth, pressure at depth. Right? So maybe if I wrote it this way, so notice in this case, P2 is the pressure at depth. P1 is the pressure at the water surface. That's cool. Well, crap. How can we get P1? P1 is the pressure at depth for the oil column, right? So P1 must equal, what's the pressure at the surface for the oil column? P0. What I'm going to do, I'm going to stick the whole word oil on this one just to clearly distinguish it, okay? That way you can tell that this is P subscript 0, this is P, or I just misspoke, that's rho subscript oil. G, depth of the oil. So when I plug all that in, notice, and maybe what I'll do is just to emphasize this, there's an atmospheric pressure component plus, I'm just sticking this up into here, there we go. So I just wanted to point out that you can actually even do this multiple times with multiple fluids and stack them and add them and it works out. So far, so good? All right. What should we be careful about when we plug in the numbers? Centimeters, right? So we got to watch out. Centimeters are not going to be our friends. So what should I plug in for H oil here? 0.12 meters. Oops. 0.08. And I'm being lazy with sig figs. Who cares? Okay. Yes, question.
The depth of the water, is it the 8 centimeters close to 12 or just?
No, it's just the depth of the actual water. So remember, in this equation here, what are we saying? You've already accounted for P1, right? There's going to be, the oil is going to affect P1. And so then we start over at this and say, okay, now P1 is here. So notice it's P1, and obviously the height of the oil column does matter, right? The more oil you have, the bigger P1 is, the bigger P2 is.
So where it's green, P not, is that supposed to be?
That's from the atmosphere, right? And so do you agree atmospheric pressure is the same as the top of the oil surface? So that's why I changed this to green right here, because the surface of the oil is the same as the atmospheric pressure. Got it? And so all of this, maybe if I just drew it like this. So what I'm doing is I'm saying, look, whatever I had at P1 at the bottom of the oil column, I got to add this to it. Is that, you good? Yep, yep. Good question. Been a long class already, hasn't it? I wish I had another problem. Damn. Look at the next problem. Damn. I would like to do this problem, and yeah, I'm going to. So I'm going to do this damn problem. Okay, 14.8, and then we'll take our break after that. Or I don't know. Do you guys need a break now? Is this? Can we take our break? What do you want? Let's do this damn problem. All right. I need to do this over here. I think this is interesting. You'll like this. I'll go quickly. You got the solutions written up. Just erasing the board, Zoomers. Always better to have the second half of class be short. 14.8. Got some rocks here. Bedrock. I'm going to use a rectangular slab. This is rock. This is the dam. Okay, so it's a piece of concrete. There's some fluid in here. Okay. The pressure at the surface is probably atmospheric. We're assuming normal weather conditions, okay? We have atmospheric pressure. What's the pressure at the surface? Right here. If the air is at atmospheric pressure, what's the water surface at? Same. We know the equation for pressure versus depth is going to be P naught plus rho G H, where H is the depth. Do you agree that's increasing linearly with depth? There's no squareds or cubes or EGX or sine or cosine, right? So it should start out like this. And it's going to get a little bit longer, but the change is going to be linear. And the pressure is going to increase until we get to the bottom. On average, I want to point out that the average would be half of that total. We could use the average depth would be H over 2. I guess I should be clear here. I'm assuming this water has depth H. Okay. On average, the water pressure average is going to be P naught plus the average depth. I hope you guys could buy into that. Are you good with that? if it's varying linearly, the top has no GH, the bottom has full rho GH. On average, it's going to be rho GH over 2. Okay. Now outside, there's still air molecules over here. So there's going to be constant pressure on the other side. Now wait a minute, I thought the pressure increases with depth. Air is compressible. Remember, the whole point of this stupid water hammer was to show you, as long as the density is going to remain constant, right? We're going to assume this pressure versus depth equation is valid. But for air, it's just a different fluid. We do not want to use this equation for the pressure associated with air. Got it? It's a different material. Okay. That's why the air pressure remains constant over here. The changes in distance here are not going to cause a significant, right? You're not going to stop breathing if you go to the top of the dam. You have to go several miles in the air before the atmospheric pressure changes significantly. Okay, or at least a mile or so. Okay, well, check this out. What I'm most interested in is I do not want this dam to fail, right? I want to make sure, what force does the bedrock need to exert horizontally to keep this dam from blowing out? Okay. Well, whenever I have a pressure difference, I could get a force due to the pressure difference, and that's equal to delta P times the area. And in this case, that force is going to go from high pressure to low pressure. I hope you agree it makes sense that the net force is going to point in the direction of high pressure to low. Is everybody cool with that? And do you agree, if we don't want this dam to be moving, the force associated with that pressure differential must be balanced with this force of the rock? So this gives us a simple version of a dam, where it gives us an idea of how much force needs to be exerted on the dam to keep it from blowing out by the bedrock. Obviously, there are forces up and down. We're ignoring those for now, okay? I'm worried about the lateral forces. Okay, well, in this case, the pressure difference, if I plug in the average pressure here, the pressure difference gets rid of the P naught term, and I get rho G H over 2. And now I need the area of the dam. The area of the dam, got to be careful here. Let's say this is the thickness of the dam. The area is not H times T. That's a cross-sectional area here, but that's not the area that the pressure is pushing on. Do you agree? So if you look, if we do a top view of the dam, this is a top view. We're told that that dimension is D, and there's the thickness of the dam. I hope you agree that the area is actually H times D, where H is the depth and D is the width or dimension into the page. Cool? This is the whole point of this. It's times HD. Look at this cool result. It depends on the depth squared. So notice, these are the parameters that a dam builder would need to think about in order to keep this dam from being tipped over or at least laterally shifted. Doing all right with that? So that's got to be the force exerted laterally by the rock. related to this question. Imagine you have two dams from an aerial view. Let's say one of these is holding back Skinny Lake in a river. This is dam 1. Here's dam 2. This one is holding back a massive lake. Okay, dam 2. You have the same depth. Same dam cross-sectional, I should be careful. Same dam areas. How about that? Which dam is going to take more force? 1 or 2? The one with the big lake behind it, or the one with the narrow river? Which one's going to have more force on it to keep it in place?
Second.
No, the same.
Same.
This is the point of it. The dam area is what determines how much force, not how much water is behind it. Crazy, right? Isn't that weird? Think about this. If you're building a dam, what do you really want? You want some place where the canyon gets really narrow, but then it opens up hella wide back here so you can store a lot of water for the same amount of concrete without it blowing out. Cool? I know you want that break. Which has greater density? 100 kilograms of lead or 100 kilograms of aluminum? Which has greater density? Listen carefully. Which has greater density? 100 kilograms of lead or 100 kilograms of aluminum? Which is more dense? Lead, right? And then what's the other one? Which has greater volume? 100 kilograms of lead or 100 kilograms of aluminum? Which has greater volume? The aluminum. All right, take your break. Just keeping you honest. All right. Okay, I appreciate your hard work. I know it's kind of tiring sometimes. I want to show you something weird. Go over here to 8. Is that the right one? Okay. I think I can get your head out of it. You're good. Okay. So I call this funky tube. By the way, we're on page 130, problem 14.11. The funky tube. All right. So hopefully you can see this on Zoom. Am I on the right one, Alan?
Yeah.
All right, I got some water in here. Now this happens kind of quickly, so just kind of watch it. Just observe as closely as you can. In particular, observe the water levels as they bounce around a bit. Did you see they kind of bounce around and then stabilize? I'm gonna pour a little of this out. Whoops. That's not right. So now, whatever, close enough. Let's take this over here. Let's go to this one. See a little bit better. Okay, you see the tube with water in it, the funky tube? In particular, what I want you to notice about this funky tube is regardless of the shape, do you agree that the water is at the same depth in each one? Right? And so I like to think about this by imagining a small section of water that's right here, a small chunk of water right below that nail there, right? Or right here. In this case, we know that this water on average is not going left or right. Do you agree? Therefore, what must be the pressure on each side of this little chunk of water right under that nail? If it's not moving around, the pressures are the same, not 1 atm. 1 atm is the pressure at the surface. And then what matters is not the shape of each tube, not the curvy shapes. All that matters is the depth. And I argue this verifies that the pressure depends only on the depth. Do you agree? Right? It's not the shape of the tube that matters. Right? It's not how much volume is in here. Each one of these has a different volume, a different shape, different amounts of bends. But we say water seeks its own level. Pressure is a function of depth. Now, to be clear, this water is not moving. So still or motionless water is seeking its own depth. Good with that? All right. All right. So that's kind of a verification of what we were just doing before. I probably should have done that first, but I didn't. I forgot. Now I want to talk about hydraulics. I was showing you this earlier. Whoops. And maybe I'll do this while I got it here. Give me a sec. Okay. Are we on, Alan?
Yeah.
Good, thanks. Oh, geez. Okay. Here's a simple hydraulic system. And notice something here in particular. Look at the amount of water that is changed in each cylinder. Obviously, this one that I'm tapping in my right hand has a larger diameter. The one over here in my left hand has the smaller diameter. Notice it travels more distance. Do you agree? This is a lot like the force distance trade-off we've been talking about, except now we're talking about a pressure area, or sorry, a force area trade-off. If these are at the same exact depth like that, the pressure in each column is the same. Agreed? So if we have the same pressure in each side, I need different amounts of force. The larger area, I would have to push harder on it to make this side go up than the other side. Wait, let me just draw a picture on the board because this is getting too many words. Problem 14.12. Hydraulics. We're going to have a small diameter piston. There's going to be Esmeralda standing on top of here. Okay. The mass of Esme is, what did I say? 45 kilograms. This piston, I'm going to use a lowercase d. Or the small diameter piston is what, 20.0 centimeters, right? Then there's a fluid-filled chamber. So if we use the same color as our hydraulic press a second ago, and this one's a little bit bigger, I think. The large diameter piston was what, 63.2 centimeters? And the idea here is we're going to have a piston, and these two are going to be at exactly the same depth. That means they're going to have the same pressure. Furthermore, I'm going to put some uranium on here because it's fun. Why not put a giant chunk of uranium on your local hydraulic press? And maybe Esme's wearing a triply faked lead suit to avoid this. It's depleted uranium. Okay, yay. We'll just put a U over here. What I'm curious about is what is the mass of uranium that can be supported? And finally, I believe we're told that the mass of the pistons themselves is negligible. So we don't have to worry about the mass of the piece of metal that she's standing on, or the mass of this piece of metal that the uranium is sitting on. Cool? Just ignore those. Well, if we have the same pressure, the pressure at Esme's side should equal the pressure on the uranium side. PU. How can we get pressure, and how does that relate to force? How does pressure relate to force? What's the basic equation we used at the very beginning? What are the units? Newtons per meter squared. How does this relate to force? Newtons per meter squared is, yeah, that's what I was looking for. Sorry, we have so many equations, I realize that's difficult. Sorry about that. Maybe I'll draw Esme with blue hair here so we can keep track. Okay. Now in this case, do you agree that the force that Esme exerts is just mg? Right? And the force of the uranium would be mass of the uranium times g. What's the area in terms of the diameters? How does area relate to diameter? Do you remember? Week 1? What's any, if this is a circle, what's the area of any circle? Pi r squared. And then when you have a d, you got a d over 2, you square it, you get a d over 4, right? That's all. You know what is pi r squared. I'm going to call it pi d squared over 4. You know what I'm saying? That's all I was trying to get at. You're probably overthinking that. This is the big diameter, so it's pi big diameter squared over 4. The over 4 comes the over 2 squared. When I work all this out, what's going to drop out at this stage? G, what else? pi, what else? I'm golfing, I'm about to swing, I say. Now, when I rearrange this, notice we get these diameters squared. The mass of uranium is equal to the mass of ESME times some factor. In this case, it's going to be capital D squared over little d squared, or the diameter ratio squared. Take a second to believe that. D comes up top, and then I took the square outside, because they're both squared, d squared and d squared. Well, in this case, let's plug in some numbers. For these diameters, notice it's okay to use centimeters for this problem because the units of centimeters drop out before you square it. So 63.2 divided by 20. I'm going to square that. And I got about 100. 99.9. Wait, let's see. No, I got a factor of 10, 9.99. Sorry about that. The mass of uranium is approximately 10 times the mass of ESME, or 450 kilograms. So what is the point of this? A small applied force can be used to hold up a large mass. I know it seems cheesy, but geez, this is hugely useful, hugely useful. Now, some people probably ride bikes or walk to school, but a lot of you probably took the bus or drove, right? I want to point out something interesting. At some point on the drive today, you were probably driving 50 miles an hour or something, and you needed to stop your car. What did you do to stop the car? Or what did the bus driver do to stop the bus? What actual action did they take? They wiggled their toes a little bit, right? Isn't it crazy that you can wiggle your toe and stop a 50-mile-an-hour moving vehicle that weighs 1,000 pounds or more? Hydraulics are at work. I know this is going to seem a little crazy, but I got a simulation here. Let me get the screen there. Oops, I forgot to turn the screens on. Let's just sit here in the dark and reflect on life. How strange it is that we're all sitting in this classroom doing physics problems on purpose. That's a weird thing to do, people. That one not turn on? All right, so hopefully you can see on this left side, Zoomers, you can see, I hope. By the way, Zoomers, definitely come to class in person next time if you want to see the cool stuff, because not everything can be shown here. But so in this case, whoops, I just want you to maybe think about this. This is where your foot is applied, right? You're going to step on a brake pedal, and then basically we use a hydraulic system similar to the hydraulic press and or like those syringes I was showing you, right? And so you push on one piston that causes some other pistons to press against the rotors or your brakes, right? So you have the brake caliper pistons are pressed against the rotors when you push a cylinder and apply this hydraulic system. I don't know. So I think that's slightly interesting. And when you think about it, you could, in theory, figure all this stuff out. I don't know anything about the real world, and the realities of working on cars are much different than the basic physics principles. But I do find it interesting that you could kind of understand why these hydraulics are used, and you could use it as a force multiplier so that you could actually apply enough force to stop a vehicle. Is that enough on that? The other interesting application would be jacking your car, meaning like raising it up so you could fix a flat tire. Take a look at problem 14.13. I will turn the lights on and get rid of the screen so you can look at it. Oh, that's slightly interesting, right? To me it is. So you could start looking at 14.13, and you could imagine it's basically doing a chapter 12 statics problem where you have a rod with a pivot and you apply a force, and then you use a lever arm to magnify the force, and that allows the force from your hand to lift a vehicle off the ground. It's pretty amazing when you think about it, right? What I'm saying is the same principle. Instead of having a person here, what if you did this? And there's a little lever here. So if we skip this, what was the next problem? 14.13, I'm assuming. You can put a pivot point here and attach this to the piston. And the idea is you could apply a small force here. You get a lever arm multiplier here that pushes down on the piston. So for a tiny force from your hand, you could actually lift an entire vehicle this way. Cool, right? All right, enough said on that. Hydraulics are interesting. Take a look at 14.14 on page 132. That's this problem right here. Right? Whoops, where am I? I'm right here. All right, it's kind of hard to do this on film here. And all I'm trying to do is show you, if you look at that one, notice that there's, oh gosh, the lighting is terrible. But I just want to point out, hopefully you can see that with double the area, you get, let's see, excuse me. With double the diameter, you should get, let's see, 4 times the distance traveled. But that's what I was talking about there. If you care, that's great. You can draw it. If you don't care, you can look at the solutions and move on. Whew. All right, we're doing all right here. How's everybody doing? Questions? I have a few loose ends to tie up this lecture, and then I'm going to foreshadow the next one, and we're out of here. Okay? So I want to talk about tire pressure. I know this seems strange, but I think it's important to discuss reality when we're doing a physics class whenever we can. So many things in the real world relate to these fluids and pressure. I want to make sure you understand them. I'm looking at the bottom of page 132. Is anybody in here a chemist or a biochemist? Is that anybody? Maybe you, right? So this is probably important for people that have to do chemistry, all right? So imagine you have a tire here. We're going to do a normal automotive tire, a sedan, nothing fancy. Maybe it's a Buick Century with an antler tied to the front with neon yellow rope driving in a Santa Maria parade. Maybe this was done, maybe it wasn't. That should be the extra credit question on the test. I don't know why, but I did that once. Well, let's move on. Okay. Sorry, I'm entertaining myself remembering that moment. Pretty good time. Okay, you have a tire. Does anybody know the typical tire pressure of a normal tire on a car?
38.
What is it?
38.
Okay, 38 what?
PSI.
PSI. So I'm going to cheat and round it to 35 PSI. Okay, you cool with that? Depends on the vehicle, depends on the tires, depends on a lot of factors. But 35 PSI, some people might say 32, 38, somewhere around 35 is pretty good. That is not the pressure in the tire. This is the pressure on the gauge. Okay, 35 PSI is what the gauge reads. Now I want you to think about this. If we had a pressure gauge here, this is my attempt to draw that. Maybe you know these pressure gauges where there's like a little stick that comes out and there's some lines on it. Okay, so 35 PSI is what that gauge reads. Now I want you to think about this. What is outside the tire everywhere? Air. We're going to assume that that is P0. So now in this case, the gauge is actually reading the pressure difference. Now, if you recall, atmospheric in PSI was about 15. So it turns out the actual pressure inside is called P absolute. And P absolute is equal to pressure of the air, or the ambient pressure, plus the gauge. I actually like to think about it like the gauge reads the pressure difference. So what do gauges actually read? They read pressure differences, all right? So now, why am I bringing this up? For this one reason. If you're going to use the equation PV equals nRT, you're going to say, dude, I thought it was little r. We're like, this is physics. We're going to use big R, fool. Little r is for chemists. Yeah. But the other one is I'm going to say, this is not the gauge pressure, use absolute pressure. So in the physics equation, PV equals nRT for ideal gases, we need to use absolute pressures. Basically, there's going to be a number of equations you see throughout your next physics class or physics 162, maybe in your chemistry class. And it's important to know that there's a difference between what a gauge reads and the actual pressure or absolute pressure. Cool? It's just a weird fact. Enough, moving on. All right. Gauge pressures are great for forces though, right? Here's a crazy thing. How can we check this? Take a piece of graph paper, drive over it, pump up your tire, read the pressure. Then, when you have the graph paper underneath, trace out the tire. You trace out the tire and you'll get the area of the contact patch with the ground. You could do this for all 4 tires, right? Get the total area, read the manual for your vehicle or Google it and find the vehicle's weight. Make sure you're on level ground. And then you could get the force over area and see what the pressure is. Got it? So this is a lab you could do at home. If you drive over some graph paper, make sure all your tires are approximately the same PSI, rock it out and tell me if I'm wrong. Okay? Cool? All right. Oh, sweet. We made it. I was worried we were going to run out of time. Okay. Now, I want to mention another weird note on some numbers, just because I think sometimes numbers are actually helpful to learn. We talked about the density of water as 1 gram per centimeter cubed. we talked that when you convert that, it's multiplied by a factor of 1,000 kilograms per meter cubed. The density of oil, there's many types of oil. They're all over the place. Oil is less, so maybe 800 to 900. It's going to depend on the type of oil. What's the density of ice? Does anybody know the density of ice? Approximately? Hint. What's that?
500.
Oh, that's more like some wood. But maybe you heard this. How much of an iceberg is underwater?
90%.
90%. Take a guess what the density of ice is.
900.
900-ish. What's the density of air? Approximately. Anybody know? It's about 1. It's going to depend on the pressure. And so remember that air, the density is going to change a lot. It's not like water. So it's going to vary wildly. But do notice this. It's about 1,000 times less. Approximately 1,000 times less. Okay? But it's not 0. A strange fact that I read once. Depending on what size refrigerator you have, the amount of air in your refrigerator weighs approximately as much as a dozen eggs. And it's like that right now. Think about this. Think about the air inside a typical refrigerator. It's probably about a meter cubed, right? Like, think about this. Right? The air inside a refrigerator, yeah, it's easily as big as this cube, right? So, okay, or if you will, you can think about this desk here. I know Zoomers, you can't see that. Right, the air here, this is about a meter times a meter times a meter. So, right, all right, so this is reasonable. That's a couple of pounds. Kilograms, about 2.2 pounds. Maybe you've lifted weights in the gym, right? What's a plate in the gym? It's 45 pounds. How many kilos? Yeah, about 20, and you get 45, right? So 2.2 is approximately the number you multiply by. So anyways, yeah, this is a couple of pounds. I find that slightly interesting. I want you to think about something. When you jump in the water, when you're swimming around, you feel a buoyant force, right? You float. We're going to talk about that in just a second. The buoyant force associated with swimming around in the pool is going to depend on this density right here. But now, imagine that we're all swimming in a sea of air. We are. We actually have a buoyant force up from the air. Well, why don't we notice it? The density is 1,000 times smaller. So we do have a buoyant force on us all the time from swimming in this sea of air. It's just negligible compared to the buoyant force when we jump in the water. And so all semester long, we've completely ignored this because it's completely negligible for most situations. But imagine if you were doing a very technical scientific measurement, maybe the buoyant force due to air would start to affect your measurements in the 4th sig fig, right? Because it's 3 sig figs over. It might have, so if you had to get a mass right to 4 sig figs or 5, maybe you actually have to account for the buoyant force due to air. All right? Speaking of buoyant forces, where am I going to put this? Let's put it right here. We're going to talk about this next time, but for now, I want to talk about this buoyant force. Just to foreshadow it, so we're not starting from nothing. By the way, this is on page 135. The buoyant force is going to depend on these factors. We already mentioned it's going to depend on the fluid density. This V displaced notice I try to use a capital V. That's just my style. G is your old friend. Little g. Okay. These problems should be hella easy. And in fact, they end up being confusing for reasons I'm about to show you. Getting a number for fluid density, that's just a number. G is a number. All the confusion comes with the displaced fluid volume. So I want to show you some scenarios now. Call class today, and then we'll pick up here next time. So first, let's look at these examples over here. All right. So here we have some water in a tank. Now, I was feeling frisky, so I threw in a little bit of salt. Okay, this is not fresh water. I put in just a tiny bit of salt. By tiny bit, I mean 2 cans. So about 1.5 kilograms of salt. All right, for reasons I'll discuss in a minute. Now, when you put some objects in here, do I have my tape? I'm just going to put a reference level on here. Is that pretty close to, you can see better than me right there. Does that look like it's approximately with the water level? Yes. Yeah. Okay. So we're looking at the bottom of the tape is the water level. Okay. Zoomer, is that showing up at all on Zoom, Alan? All right. Yeah. All right. So now, let's say I take some wood and throw it in here. Watch the water level. This is a tasty looking soup here. My kids would love this demo. Do you agree the water was displaced upwards slightly? Now, I calibrated this. It looks like, and this is not being used right now. That was a different water level. Oh, that's how many drops I was supposed to use. Whoops. Okay, never mind. I just remembered something. That was a note I was supposed to read earlier. Whatever. So 6 centimeters is of depth in this particular volume of water corresponds to 8 liters. So just kind of looking at this measurement, looks like it went up about 2 centimeters. So 2 centimeters, that's 1/3 of 8 liters. Oh, geez, that's a couple of liters. Got it? So in this experiment, I displaced a couple of liters, about 2 1/3 liter, or 2 2/3. I forget what I said. I displaced it 8/3 liters. You could convert that 8/3 liters into meters cubed and plug it in to find the buoyant force. Here's my question for you. Is the volume of displacement, that 8/3 liters, is that equal to the volume of the wood? Yes or no? What do you think? No, right? Not all of the wood is underwater, right? And this is where the problems get tricky. Students will want to say, well, I'm just going to take the volume of the wood. I stuck the wood in the water. The volume of wood should be the volume of fluid displaced. Not true. It's some fraction of this volume because not all of the wood went under the surface of the water. Got it? That's one issue. Now, to be fair, some problems come on, blocks. What if I just have some iron and I put this in there? Now, obviously the hook is sticking out, but compared to all of that iron, do you agree the hook is negligible? So in this case, the entire volume is submerged. And this is where it starts to get tricky. We see that in some problems, for objects that are floating, the volume displaced is not the volume of the objects, but for objects that sink, the volume displaced is the volume of the objects. One last one. Let's say we have the SS Jorstad here, a little boat. And this is an iron ore tanker. Coming out of Duluth, don't you know? Maybe it's the Edmund Fitzgerald too. Anybody know that reference? And I'm getting all kinds of extra credit questions out of this. I'm not giving you an extra credit question. Edmund Fitzgerald was a famous iron ore taker on the great lake they call Gitchagoonie, Lake Superior. And it was going from Duluth to somewhere, and it sunk, and they killed everybody. And then Gordon Lightfoot is a musician who made the song about it. Look it up, Edmund Fitzgerald. Dom?
The Edmund Fitzgerald.
See, one person knows, yes! The other old person. Anyways, so this is Edmund Fitzgerald too, all right? Now notice this. The whole point of this, what is the volume displaced here? Obviously I could measure it, but if I was on Lake Superior, I'm not going to be able to measure the volume in the lake. I can't see how many millimeters the lake goes up. I need to understand the displacement volume in terms of these properties. It's not the volume of the iron ore. It's not the volume of the bucket. It's a partial volume of the bucket. And so the main issue that we're going to talk about next time is how to get volume displaced right when we're doing the buoyant force. Does that make sense? Quick question for you. If I take the iron ore out and dump it in the lake, what should happen to the water level of the lake? We'll have to discuss it next time. That's it. That's a problem for next time. It was the pride of the American side. Okay.